1059, all paths from source lead to destination. So let's first try to understand the problem. We are given the axis of directed graph, where axis I means AI to BI, indicates there is an edge between nodes AI and BI. So let's just try to understand it. So if we have the edge like 0, 1, it means there's a direction from 0 to 1. 0, 2, there's a directed edge from 0 to 2. Yeah. So excuse me. And we are also having a source and destination. Yeah. So what we are going to return? Return true if and only if all roads from source leads to destination. So for example, 0 is the source. We're gonna check all the paths. So if all the paths can lead from the source to the destination, so we're gonna return true. Yeah. So at least one path exists from the source node to the destination. So this means that there is always an edge from the source to destination. So if a path X exists from the source node to a node with no outgoing edges, then that node is equal to destination. Yeah, so this means if the path exists from the source, so for example 0 to 2, yeah, from the source node to a node with no outgoing edges, and for this node 2 there's no outgoing edges. Yeah, so this 2 is the destination. Yeah, this is so difficult to pronounce. Now let's try to understand how can we solve it. Yeah, normally if we start from the source to destination, it's going to be difficult. Why? Because if you are checking from this source 0, you're going to check if this source 0 can go to 1 or go to 2. But if it can only go to one destination, it's going to be okay. But if there are other edges, for example, it can go to 1, but it can never go to destination, so we're going to return false. Yeah, but there will be a lot of checkings for us. Yeah, because definitely, if the graph is like that, let's just make a graph. Yeah, so this is the source, and this is the D is the destination, and it is the directed graph. So there are a lot of check. We have to check all the cases if it meets the condition. All the paths from the edge from the source can go to the destination. But one of the most used techniques in graph is we can reverse the edge. Because if we reverse the edge, the problem is going to be much easier than we expected. So now let's just try to check if we can reverse the edge. So what about if we reverse the edge from the destination to the source? Yeah. So for the destination, there will be always one destination. So if there are two another node, yeah, definitely it's going to be wrong. So there's only one node which has 0 outgoing edges. So for this node, for example, this node, this is the node B. So for this node B, there is 0 ingoing edges, and there are 2 outgoing edges. So this is okay. So if there's only one node, this B can go to the source A, definitely we're going to return true. If it cannot, we're going to return false. So this means if we reverse the graph, the problem is going to be much easier. We just need to use the topological sort to solve the problem. So we are going to start from the destination, this node B, and then we're going to loop through all of the nodes. And for the next BFS, we go to those 2 nodes, yeah, and then it will go to the source. So if we find the source, definitely we find all the paths it leads from the source to destination. Yeah, so we're going to return true. If we can never go to the source for the topological graph, topological sort, so we're going to return a false. Yeah. So now let's try to understand it by writing the code. So normally I'm going to prepare a graph and integrate. So the graph is going to be a default list, and with list inside, it's going to be adjacency list, and the integrate is going to be 0 times n. N is the number of nodes. Now I'm going to prepare the graph. So for AB, 2 vertices inside the as is, I'm gonna prepare this directed graph. So for AB, so 0, 1, so it's gonna be dA dot append with node B, and for the integrate, it's for the integrate it's the same. Integrate it's gonna be B, integrate with B, gonna plus equal to 1. So currently we've already prepared the adjacency list and integrate. Now let's just try to check what is inside of the queue. Definitely inside of the queue it's gonna be the queue, and it's gonna be the destination because we are starting from the destination. Yeah, but before that we need to check if there is a destination or not. Yeah, so we have to check the destination node. So we can check it by using this because the integrate has already prepared for us. Yeah, so we're gonna check the destination. If this integrate with the destination node, yeah, if it has some value, for example, if the integrate for the destination node is 1, yeah, definitely it's gonna be wrong. Yeah, normally for the destination, after we reverse the graph, so for example, this is the source and this is the destination, and we have an edge connected. Yeah, so this is the 0 and 1. Yeah, normally the source would be directed to the destination, but we're gonna reverse the graph. So if we reverse it, yeah, so the integrate for the destination should be 0, and then we're gonna start from the destination. Yeah, but even after we reverse it, the integrate for the destination is 1 or more than 0. Definitely we cannot. Yeah, definitely it means there is outgoing edges from the destination. So this means it is wrong. This cannot be a destination. Otherwise we're gonna check it as a destination. Yeah, I hope we should understand it, because there's always a path from the source to destination. So after reverse the graph, we're gonna check from the destination. Yeah. So but what if there are other nodes? So for example, this is the destination, and this is the source, and the graph has already been reversed. So for here, this one gonna be like this. Yeah, this is for example 1. So after reverse, this is node 1, and this is node 2, and this is node 0. Yeah, so after reverse, we're gonna check the destination. So for this destination, the integrate is 0. It is okay. But while we are using the topological sort, can we check this source? We can never check this source, because inside of the queue we only put the destination inside. We didn't put this node 1 inside. This is why we can never reach this node source. So it means we're gonna return a false. Yeah, because this one gonna never be inside of the queue, because we only put the destination inside of the queue. Yeah, this is why after reverse we can use the topological sort to solve the problem. Yeah, and for other cases, for in this example 2, as you can see that. So after we reverse, so there is an edge, right? So this gonna be reversed, and this gonna be reversed. But anyway, here gonna be a loop, right? Yeah, because here is a loop. This destination is okay. We're gonna pop it out of the queue. But for here, we can never pop 1 or 2 out of the queue. It means we can never check this source 0, so it's gonna be a false. Yeah. Now let's try to understand this one. This one we've already explained. Let me, just check this one. Yeah, if we reverse it, as you can see that, if we reverse it, yeah, we can directly use topological sort to solve the problem. First of all, we're gonna pop this 3 out of the queue. We're gonna put 1 and 2 inside of the queue. We're gonna put 1 and 2 out of the queue, and we put 0 inside of the queue, and we can check the result. Yeah, if we can check 0, it means 0 inside of the queue. It means we're gonna pop it out. If we pop it out, it means we're gonna check this 0. Yeah, if we can find this 0, definitely we're gonna return a true. Yeah, because after reverse, that is all the possible paths. Yeah, maybe you think, what if there is another path from 0 to another one? Yeah, if there's another path, for example, this is 4, 0 directed to 4, so definitely 0 is not a source, right? Yeah, it should be wrong. Yeah. Now I think we can start the problem, because if it is set as source, so by default we think this is gonna be a source. There will be no outgoing edges. Yeah, let's start to check. At least one path exists from source to destination. If a path exists from the source node to a node with no outgoing edges, then it is the destination. Yeah. So according to the description, if it is a source, definitely it is a source. There's no outgoing edges. If it is a destination, definitely it is a destination. There's no outgoing edges. Yeah. I'm sorry, for the source, there's no ingoing edges, and for the destination, there's no outgoing edges. Yeah, because this is definitely according to the definition of this source and the destination. Yeah. So if everything's okay, we can continue to solve the problem. So this is our queue. Now I'm gonna pop it out. Yeah, but from here, I'm gonna check if this destination has some value, so I'm gonna return a false directly. Otherwise, I'm gonna check the queue. So while queue not should equal to q dot pop left, and then we're gonna check the neighbor. So for neighbor in G with this node, and we're gonna use the integrate with this neighbor gonna be minus equal to 1. So if we integrate with this neighbor equal to 0, so this means we're gonna put it inside of the queue for this neighbor. Yeah. Finally, we're gonna return a false if we cannot return true. But from where we can return true, we can check this node. So if the node equal to the source, yeah, definitely we're gonna return a true. Otherwise, we're gonna return a false. Yeah. So this is gonna be the entire code. I hope you understand it. First of all, we're gonna build the adjacency list and the integrate, and then we're gonna check the destination. So if there's some value inside of the destination, it means there is an integrate for the destination after reverse, and definitely it is wrong. We're gonna return a false. Otherwise, we're gonna put the destination inside of the queue, and we're gonna traverse the graph by using BFS. If we find the source, we're gonna return true. Otherwise, we're gonna return false. Let me check why it is wrong. Yeah, for the first and the second testing case it is okay, but for the third case I get it wrong. Let me check. Source and destination. Yeah, I think I forgot to reverse it. Yeah, let me just check. So this is a 0, 1. So A, yeah, so B should append A because I forgot to reverse it. So with graph B should append A because I needed to reverse it. Yeah. So if I reverse it, so this is AB. So integrate A should plus equal to 1 because I have to reverse it. Yeah, you know. Now it seems the case 3 is okay because I've reversed the graph. If I didn't reverse it, this is totally not okay because this is my destination. I needed to reverse it. Yeah. Now let me submit it to check if it works. Yeah, let's just wait for a few seconds. So sometimes it's going to be really slow for the networking, but as you can see, the speed is going to be really fast. It is 94% of all submissions. Yeah. Now let's analyze the time complexity. Normally for the topological sort, the time complexity going to be OE plus V. E is the number of edges. Let's check the number of edges, 10 to the power of 4. And the number of vertices is also 10 to the power of 4. So the time complexity going to be ON, 10 to the power of 4. Yeah, and specifically, you can say that it is OE plus V. Thank you for watching. See you next time.